We are happy to have Tom Braden from UMass Amherst. He's going to talk about modular perverse sheaves on symplectic singularities.
Thanks very much. Thanks to the organizers for a chance to speak. Just one sort of technical thing. I had some kind of a disaster. My monitor stopped working from my laptop, and I'm not sure if it's the docking station or something else. And so if and everything else is connected to the docking station. So if my mic goes out or something weird happens, yeah, start waving your hands and yeah, I'll try to figure it out. But I'm slightly worried that things are kind of crashing down. My iPad, I think, is going to be solid, so hopefully the slides will be fine. Okay, yeah, so I'm going to talk about the work I'm going to talk about is not super new. It's some work I did with Carl Mautner a while back, and then I spent a number of years working in sort of combinatorial things, and I'm coming back to these questions. So this was sort of this talk is partly an opportunity for me to sort of get back to these questions, which I've been interested in for quite a long time. Okay, and I also want to sort of put them in a broader context, because basically what we have are two examples, and we're hoping that there's a more general pattern that applies to a larger class of symplectic singularities or symplectic resolutions. Okay, so the first slide is just generalities, talking about the setting in which we're living, and then we're going to talk about two particular examples of these. So I'm going to talk about conical symplectic singularities. I'm not going to assume that they have a symplectic resolution for the moment, but so we're going to talk about we're going to be worried about affine varieties with symplectic forms on their smooth locus. And you want to have a conical action. This is a technical condition which makes things work nicely. So you want to have a C star action, torus action, contracting your variety to a fixed point, and should scale the symplectic form with positive weight. And the most important thing to be a symplectic singularity is that there should be a resolution of singularities such that if you pull back the symplectic form, this is an algebraic symplectic form, not the differential geometry sense, but actually in the algebraic geometry sense. When you pull it back, it should be a regular 2 form on the resolution. And there's a theorem that says, in fact, if it's true for some resolution, then it's true for all resolutions. So you can make any resolution you like to check this. But the pullback is a regular 2 form, but it's not necessarily not degenerate. So that's a further condition which sometimes is satisfied, but it doesn't have to be. And so a lot of the beautiful varieties that show up in geometric representation theory are of this class. So the nilpotent cones of reductive groups, and more generally, you can take slices to orbits in nilpotent cones, or possibly normalizations of orbit closures. So these all have these, generally have these properties. Nakajima quiver varieties, hypertoric varieties, which are going to be the main example that I'll talk about. You can take the quotient of a symplectic vector space, which you can think of as T star of a cotangent bundle of a complex vector space, modulo a finite subgroup of symplectic morphisms. And you can take slices to Schubert varieties in the affine cross-Monte. And there's a lot of overlap between these cases, especially in type A. There's nilpotent cone singularities, Nakajima quiver varieties, and affine Schubert variety slices are more or less the same thing with appropriate indexing. And in low dimensions, many of them are also hypertoric singularities and so on. So, but in general, these are different classes. Okay, so and the next question you can ask about these things, there are two important extra pieces of information that you would like to have. Not all of these examples have them. But you might actually want to have a resolution such as the pullback of the symplectic form is symplectic. So it's not only regular, but it's non-degenerate when you pull it back. And that's a much more special thing. For example, the finite quotients of the symplectic vector space rarely satisfy this. There are many more symplectic quotient singularities that don't have resolutions. And you could also ask for a nice torus action, an action of an algebraic torus, which preserves the symplectic form. So unlike the conical action, which is scaling the symplectic form, for the T action, I want to preserve the symplectic form, and such that the fixed points are just the center point. And again, many of these, some of these have them and some of these don't. Okay, but all of these varieties have a lot of properties in common, and Braden wrote a spectacular paper that puts a lot of these in a very general framework. He proved that any symplectic singularity has a finite stratification by its symplectic leaves, and in particular, it has a finite stratification by even dimensional strata, which is unusual in the world of stratified algebraic varieties. And that closures of strata and at least on a formal neighborhood level, transverse slices to strata are also symplectic singularities. So they're closed under natural sets of operations. And in the examples that I care about, it's actually not just formal. I don't know. Yeah, I don't know a general theorem that gives this, but in these examples, you can actually get slices to strata which are actually symplectic singularities. And also, if there is a symplectic resolution, it's always semi-small, and the cohomology of the fibers, at least with C coefficients, are 0 and odd degrees. And so these are properties that are famously true for these Springer resolution of nilpotent cones, and are one of the basic building blocks for starting the theory of the Springer correspondence. And so there's sort of obviously room to generalize this. So in particular, the fact that you have this semi-small resolution tells you that the push forward of the constant sheaf on the resolution, if you have the resolution, is going to be semi-simple. It's going to be semi-simple perverse sheaf. Well, it's semi-simple because of the decomposition theorem, and it's perverse because it's semi-small. But there's even a stronger fact that the category of perverse sheaves generated by the summands is itself semi-simple. There's not only are the summands is a direct sum, but there could not be any x's because of the even property and the even dimensional strata. Okay, now what I'm now interested in is positive characteristic sheaves, and there these things are going to fail. And in particular, the simple perverse sheaves can have extensions between them. You can have non-trivial category of perverse sheaves. It's not semi-simple. Now, the odd degree vanishing of the fibers of the symplectic resolution is true in the examples that I know, and I don't know of a general theorem for this. But the examples that I know, the fibers generally have things like paving by affines or so on. So that the odd cohomology would vanish with z coefficients or any coefficients. And the examples that I'll talk about all have that property, but that's an interesting question, which I don't know for absolute generality. But if anyone knows further developments in that direction, I'd be interested to know, because I haven't followed the whole more recent work. Okay, so the two examples I'm going to talk about are the nilpotent cone of the general linear group and hypertoric varieties. So let's start with the general linear group. So we're going to talk about the cone of nilpotent matrices in GLN, in the Lie algebra of GLN. And we have the Springer resolution of the cotangent bundle of the flag variety mapping down to N. And the Springer sheaf will be the push forward of the constant sheaf on the resolution, down to the base, but now I'm taking with k coefficients. K is always going to be a field for me, but other than that, it could be positive characteristic. And if you're positive characteristic, then the category is not semi-simple necessarily. In particular, if the characteristic is less than or equal to n, then this will not be semi-simple. But it is a projective perverse sheaf. And so it has a number of nice properties. And one thing that's still true from the characteristic zero case is that the endomorphisms of that Springer sheaf is the group algebra of the Weyl group, or in this case, just the symmetric group. So that the structure of the Springer sheaf can be very different. It's no longer a direct sum, but its endomorphisms, of course, well, that's because the structure of the group algebra is different. It's no longer a sum of matrix algebras. It has more complicated structure. So that's reflected in the structure of the sheaf. But the Springer sheaf sort of exists in all characteristics and has sort of regular properties with respect to that. And so again, in any characteristic, you can look at the functor of Hams from the Springer sheaf, and that gives you a functor from perverse sheaves on the nilpotent cone to modules over the symmetric over the group algebra of the symmetric group, because you have the symmetric group acting on the Springer sheaf. And in characteristic zero, that gives the Springer bijection between simple perverse sheaves and irreducibles of the irreducible SN representations. Now, of course, yeah, I'm using the fact that I'm in GLN here. Of course, everybody knows that the story is much more complicated in other groups because there are local systems and there are questions of cuspidality and so on, which I don't want to get into. So I'm telling the simplest possible story of Springer theory. But in characteristic P, already the simple story becomes more complicated. So there, you still have one simple perverse sheaf for every stratum, which will be for every partition of n. But some of them are going to be sent to zero when you take Hams from the Springer sheaf to a simple, and so you're going to get a bijection with a subset of the simple perverse sheaves, and you still get the ones that don't go to zero are still in bijection with the remaining irreducibles, which are fewer than the partitions of that. Okay, so if you want to really understand more carefully what's going on here, there's a modular generalized Springer correspondence proved by Achar, Henderson, Juteau, and Risch. And so it says that if you want to look at all the simples in the perverse sheaves, then G equivariant perverse sheaves on n, then these are in bijection with, well, you have irreducibles of the Weyl group, but you also have irreducibles of normalizers of Levy mod Levy for various levies. And in this particular case for GLN, the levies that matter are just the ones which are GL of a power of the characteristic. So P is the characteristic of K. So if you can decompose n as a sum of powers of the characteristic, then those are the levies that are gonna be relevant in this case. Okay, and I'm not going to worry too. This is not going to come up too much more in the rest of the talk, so I'm not going to go too much into the details of this construction. And again, if you try to do it outside of GLN, it's this similar things are true, but it's more complicated to state, more complicated to prove. Okay, what I'm more interested in is the actual the abelian category structure of perverse sheaves. So not just what are the simples and how do you index the simples, but how do you what can you say about the whole category, the projectives, the extensions, and so on. And so Karl Mautner, in I guess starting with his thesis work, used the embedding. There's an embedding of the nilpotent cone of GLN into the affine Grassmannian for G, and therefore you can relate perverse sheaves on N to the Satake category. And using that, he showed that there's an equivalence of categories between perverse sheaves with K coefficients, G equivariant on N, with polynomial representations of GLN over K, where basically the torus acts with degree n. So you can think of the standard representation, for instance, well, the standard representation would have degree 1, and then tensor products of that would have higher degree. And this is also can be described as modules over Schur algebra with K coefficients, the Schur algebra SNN with K coefficients. And this functor, if you describe this functor, it's going to send the Springer sheaf to the nth tensor power of the standard representation of GLN, and the action of Sn goes to the on the Springer sheaf goes to the obvious action on E tensor n. Okay, so I mean, of course, that doesn't necessarily mean that you have complete understanding of this category, but it gives you a lot of information about the most interesting object and I mean, if you want to know particularly what happens in characteristic 2 or characteristic 3, there's still a lot of work to do, and people don't completely understand representations of Sn, or yeah, so on. But this nevertheless is a strong window into the structure of the category of perverse sheaves with positive characteristic. Any questions?
Does there happen to be an analog of this in type C?
Carl would be able to say more. I mean, there are these inclusions of other at least classical type nil cones into affine Grassmannians, but they're finite covers. They're not inclusions. They're like finite covers of some singularities. I think there's a Char, Henderson, and Risch. Some subset of that wrote a paper using that, and but I mean, probably there is a similar story, but and I think Carl has a better idea of what it looks like, but it hasn't been written up in any complete form.
Thanks.
But yeah, I mean the lack of, if I'm not saying something about some of these other cases, is not because I know that that's not possible, but but I don't know the details. Okay. Okay, so this category of representations, whatever you want to call it, I guess I should actually say, since I said the algebra, I should say the algebra is quasi-hereditary, but this category of representations is highest weight. And Duncan proved this in sort of a very algebraic method, and then sort of the next question is, how can you do this geometrically? But in particular, the structures this gives you, well, you have the simple objects indexed by the partitions, but also indexed by partitions, you have standard objects, which you at least have some topological understanding of, although as a perverse extension by 0 of the constant sheaf on an orbit. Of course, perverse extensions are not necessarily easy to understand, but at least there's something you can write down. And dually, there are costandards, which are perverse lower stars of constant sheaves. They're projective. There are enough projective objects. So you have a projective cover of every simple, and you have these tilting objects, which are filtered, but have filtrations by both standards and costandards. Okay, so it's a very important categorical structure it shows up all over the place in representation theory. The reason for this to be highest weight is quite different from category O, where it's somehow, yeah, there's sort of a different, the proofs have a different flavor, I think. So there is a geometric proof that this category is highest weight in Mirkovich-Volonin. And as I'm going to go to general cases, other situations, there's a question of, does that proof generalize? And I don't know the answer to that. Right. So we have this highest weight category, and then the question is, what can we do with it? Well, there's an additional thing, which is that this category is not just highest weight, but it's actually wrinkle self-dual. So this says that there's a relationship between the projective objects and the tilting objects, and this speaking as somebody who likes perverse sheaves and topology, this is really important because the tilting objects are relatively easy to understand. I'll at the bottom of the slide, I say what the tilting objects are, and they're topologically very simple. Whereas projective perverse sheaves, you can construct them algorithmically, but actually understanding what the fibers are and how they're put together as a perverse sheaf is typically very, very difficult. So what the wrinkle self-duality says is that the endomorphism algebra of this direct sum of all of the projectives is isomorphic to the endomorphism algebra of the direct sum of all the tiltings. And to be more precise, the correspondence is order reversing. So it's going to take the projective for lambda to the tilting for lambda transpose. So there's some order reversing property with respect to the stratification going on. Duncan proved this for modules over the Schur algebra, again, sort of purely algebraically, but Achar and Mautner described a geometric proof of this using the Fourier-Sato transform. And it shows up in a way very similar to the way it shows to one of the proofs of Springer theory. Even character 0 uses the Fourier transform, and it's really for kind of the same reasons. The Fourier-Sato transform takes perverse sheaves on conically constructible perverse sheaves on a vector space, in this case the Lie algebra, to the conically constructible vector space on the dual vector space. But in this case, by the Killing form, this is isomorphic to G itself again. So you get a functor that takes perverse sheaves on G to perverse sheaves on G, and Achar and Mautner consider the functor, which is take a perverse sheaf on the nil cone, push it into G, take the Fourier transform, and then restrict back again, and with a shift to preserve perversity. And the first thing is that this is T exact. It does preserve perversity, and it ends up being an equivalence of categories, and it takes a tilting sheaf to a projective sheaf.
Sorry, Tom, this isn't quite right, I don't think.
Did I get it backwards?
Yeah, so we show that it's an equivalence of derived categories.
Okay.
It's not T exact, but it does take the tiltings to the projectives.
Okay, sorry. Okay, thank you. Okay, so dB. Yeah. Okay. But nevertheless, the HOMs are going to be correct. Yeah, of course, that would be, yeah. I mean, it shouldn't be a, yeah. Okay. Thank you, Carl. And in addition, the tiltings have a simple description as push forwards of resolutions of orbit closures. So the tilting that's supported on the orbit closure O lambda is going to come from a symplectic from push forward of a symplectic resolution of O lambda, and in particular, the tilting objects are parity sheaves. The stalks and co-stalks vanish in odd degrees, or degrees with the same parity, basically. And that's a general principle that when there's a general proof that if you have a highest weight category of perverse sheaves, then tilting objects end up being parity, or vice versa. Okay. Okay, so I came into the story with some interest in sort of the general category of symplectic resolutions, and Carl and I worked to see whether something similar was true for hypertoric varieties, and that's the main theorem that I'm going to talk about. So just a brief description of what hypertoric varieties are. So they're the most computable class of symplectic varieties and symplectic resolutions, where you can really compute almost everything you want to compute by hand. So you're going to start with an n-dimensional torus acting in the standard way on Cn, and then it acts on the cotangent bundle of Cn by the induced action. And the data that to go into this is going to be a rank D saturated sublattice of Zn, which is, I think of as the character lattice of the torus. So I'm going to take some sublattice of this should be saturated, so the quotient shouldn't have any torsion, and a couple more technical conditions. I want it to be unimodular, so I want it to be the image of an integer matrix where all the maximal minors are 0, 1, or -1. And then even more technical, which you can get rid of, I don't want it to be contained in any coordinate subspace or to contain any coordinate vector. Though those are not particularly important, but they just make your life easier. Okay, and so the basic construction is you have a moment map of the action of the n-dimensional torus, which takes the cotangent bundle of Cn to, well, basically Cn, which is the Lie algebra of this torus, the dual of the Lie algebra of this torus. And in coordinates, it just takes, you know, an n tuple ziwi, what's a 2n tuple of n zi's and n wi's to z1 w1 up to zn wn. And then I have a quotient of that to the dual of the Lie algebra of a group K, where K is the kernel of all the characters in this that I picked in my sublattice. And since this sublattice was saturated, this K will be a torus. It will be connected. So you can do hypertoric varieties with non-connected quotient by quotient by non-connected groups, but it makes it more complicated, and the theorem I'm going to state won't work. Won't use that case. So you have this moment map of K, which maps the cotangent bundle to the dual of Lie algebra of K. You take the inverse image of 0 and take the quotient, the categorical quotient by K, and that gives you an affine singular hypertoric variety. And then if you want the resolution, you're going to take the GIT quotient with respect to a parameter which ends up living in the lattice mod V, and needs to be sufficiently generic with respect to certain hyperplanes, which I won't write down, but in order for it to be resolution. And both of these varieties have an action of the quotient torus Tn mod K, and it's going to be it's a d-dimensional torus, and these are 2D dimensional varieties, so they sort of they have a flavor of being like cotangent bundles of toric varieties, but they're not. They're more complicated than that. But so they have a half-dimensional torus acting, and they have sort of a Lagrangian spine of toric varieties inside them. Okay, so so the geometry of these varieties is governed by the combinatorics of a certain multi-arrangement. Well, there's two arrangements, one for this affine thing and one for the smooth resolution. And basically what you do is you take the real version of this vector space V, and except I think I'm dualizing this wrong. I think I need to take the perp space here, because V is, yeah, I need, sorry, I wrote this too quickly. I basically I need the cotangent bundle of sorry, this is right, because K, sorry, I dualized twice and then I'm okay, sorry, should have trusted myself. Yeah, so the point is VR is the dual of the Lie algebra of the torus that's acting. And so if you look at VR, then it's some vector space embedded in Rn, and you take the intersection of that with the coordinate hyperplanes, and that gives you a hyperplane arrangement. And then for the resolution, you just translate this real vector space away from the origin, and so now you get a non-central arrangement, and the combinatorics of those two arrangements sort of governs the geometry of these spaces. And just a basic example, if you take the sum of x1 plus x2 plus x3 equals 0 for my V, then your torus that you're quotienting by is a one-dimensional torus, the diagonal torus in C star cubed, and your varieties end up being, well, the smooth one is a cotangent bundle of P2, and then the singular one is the contraction of the zero fiber of that, which ends up being a closure of a nilpotent orbit in GL3. Okay, so so I need to describe a stratification of these varieties, And there's a couple of different stratifications. I'm going to use the coarsest stratification around, which is a stratification by symplectic leaves. And so what you need to do are to look at flats of the arrangement, which are basically just intersections of hyperplanes. And you want to look at intersections of hyperplanes that really define a space. So in particular, in this case, I want to look at the sets of hyperplanes I want to consider are the empty set of hyperplanes, which gives me the whole space because I'm intersecting no hyperplanes, and 1 and 2 and 3 and 4 I take together because if I intersected with just 3, that would be the same as if I intersected with 3 and 4. So you take the sort of maximal indexing set you can for each possible subspace. And finally, you can intersect all of them and get the point at the middle. But other combinations of hyperplanes would give you spaces you've already seen before. So, okay. And for every flat, you can look at basically you can look at a subspace of this affine hypertoric variety, which ends up being another hypertoric variety, whose arrangement is coming from the subspace that's indexed by that flat. So if I take 3, 4, then I get this line, and in that line I have 2 hyperplanes, 1 and 2, and that's the arrangement, two points in a line, which corresponds to the subvariety of that flat. And the slice, a normal slice to a general point of one of these subvarieties is again a hypertoric variety, and it corresponds to the slice arrangement. So if I take the slice to this flat, if I take the slice of this flat, I again get a line with 2 points in it, but they're different 2 points. It's now the points 3 and 4 instead of the points 1 and 2. And that would govern the geometry of the slice to that subhypertoric variety. Okay, so finally, the stratification I want is going to be sort of the open part of these subvarieties, but only for a certain subset of flats that what are called colute free, which is basically saying that the slice arrangement, the transverse arrangement, doesn't split as a point in a line times something else. And so for instance, the flat 1 and the flat 2 are not colute free because their transverse is exactly just a point in a line. Whereas the flat 3, 4 is colute free. So the colute free flats in this case are the empty flat, 3, 4, and the whole thing. And so there will be so in this case, this example would have a stratification with three strata. Okay. Any questions? Okay, so then given this hypertoric variety, defined by this information, there's a dual hypertoric variety, a Gale dual hypertoric variety, which is also the symplectic dual or the 3D mirror symmetry dual, defined by taking the perpendicular lattice in the dual copy of Zn. And it gives you a variety whose dimension is 2n minus the dimension of the variety you started with. And as an example, if you take this the example I gave before, which is the closure of a nilpotent orbit in GL3, what you end up getting is C2 modulo the symplectic action of Z mod 3. Okay. And one of the reasons that I wanted to look at only colute free strata, there's a finer stratification that uses all flats, but the reason I wanted to only use the colute free flats is because then there's a bijection between colute free flats of one arrangement and the dual arrangement. So for example, in this 3 lines in the plane example, if I included the 3 lines as flats, then there would be nothing on the other side to be dual to them. Okay. But in this case, when you restrict to these colute free flats, then there's a bijection between the colute free flats of one arrangement and the dual arrangement, which is just taking complements. And furthermore, there's also a bijection between fixed points of the resolutions, which is going to be important later. The fixed points of the resolution are indexed by bases of the arrangement, which are basically subsets of hyperplanes which intersect to the point, to the center point, but transversely, so that there's a minimum number of such. So a basis for these three lines in the plane would be any two of the lines. So in this case, there are three bases, and there's a bijection between bases of one and bases of the other, which is actually in some sense the main content of Gale duality, which is given by taking complements. So if your bases are two hyperplanes here, then your bases are a single hyperplane in the three points in a line. Okay. So finally I have the information. I have the stratification and I have these varieties, and I can tell I can tell you what the theorem is. So the theorem is that the category of perverse sheaves with field coefficients, positive characteristic possibly, is a highest weight category, and it's wrinkle dual to the category of perverse sheaves on the dual hypertoric variety. And I should say the technical conditions here. It needs to be constructible with respect to the stratification that I gave, and T equivariant. And the T equivariance is only there because the strata are not simply connected. And another way of saying it is I want the perverse sheaves whose simple constituents are all only constant local systems on strata IC sheaves of those. So basically I want to consider the perverse sheaves that only contain one IC sheaf for each stratum, or one isomorphism class of IC sheaf for each stratum. And the tilting objects are again parity objects, which come from taking resolutions of these stratum closures, or these sub-hypertoric varieties, and taking push forwards of the constant sheaf of those. And if you want the indecomposable tiltings, you take the indecomposable direct summand of those that have maximal support. And then when you take wrinkle duality, again, there's an order reversing property. The tilting corresponding to a flat F corresponds to the projective of the dual flat, which is given by the complement. So one thing I want to emphasize here that I'll say more about toward the end is that this resolution sheaf is actually independent up to isomorphism of the choice of resolution. Now the resolution depended on a GIT parameter, and that there are chambers of the GIT parameters, and unlike in the sort of flag variety situation, the chambers are not all the same. And what happens is if you take this arrangement that I gave before, there are different ways to blow it up to a simple arrangement where the hyperplanes intersect transversely. You could do it this way, or you could do it this way. And they are not, the corresponding resolutions are not isomorphic as algebraic varieties. They're diffeomorphic abstractly, but they're not the same algebraic variety. But they have the same cohomology. And so, and stronger statement, which we prove, which is one of the important ingredients in the paper, is that in fact this resolution sheaf itself, not just the cohomology of the variety, but the push forward sheaf is independent of this choice of resolution. Okay, so we have tilting objects, but in order to talk about wrinkle duality, we also need projective objects. And the way we access the projective objects, again, they're topologically hard to understand, but we access them by constructing projectives that represent certain exact functors. And the exact functors are going to be exact functors from perverse sheaves to vector spaces. These come from hyperbolic restriction. So I'm going to take a co-character of the torus such that the fixed points of that co-character are one of these MFs, one of these stratum closures. And there is such a for any MF there is such a, actually, even if it's not co-loop free, there exists such a co-character. And then you take the attracting set of this co-character and take the star restriction to the attracting set followed by the shriek restriction to the fixed point locus. And a theorem which we prove is that this is T exact, and then you can take the stalk of this, and it will preserve the stratification and preserve equivariance. So it gives you a functor on these categories, and then you can take the stalk at a generic point of the fixed point locus, and that gives you the exact functor that you want to vector spaces. Okay. The fact that this functor is T exact, well, the first thing you look at is the case where the fixed point is just the center point, and then the fact that functor is T exact is basically follows from an argument of Mirkovich and Volonin. The point is that the attracting set is Lagrangian in every stratum, so it's half the dimension of the stratum, and that plus a little bit of playing around with hyperbolic restriction formally implies that functor is exact. And then to show that the functor is exact even if you're restricting to a larger fixed point set, well, it's going to be exact restricting to a generic point by because you can restrict to a normal slice and use the same argument. And then for the general thing, there's some relationship between these functors, which I won't go into details of, but yeah, but the key ingredient is argument of Mirkovich and Volonin, which they used for geometric Satake. And a second important point is that this functor that I wrote down, well, so the hyperbolic restriction functor, even before you restrict to the generic point, this hyperbolic restriction functor does not depend on the choice of co-character once you fix the fixed point locus. However, the attracting locus definitely does depend on it. So again, this is a non-obvious property that there's some chamber structure. If you look at the set of all co-characters that have the right fixed point locus, there's going to be some chambers, and you sort of want to understand what happens. Why does it not change if you cross a wall? Any questions? Okay, so how do we approach proving this theorem? We basically take all of the exact functors that we have lying around and all of these resolution sheaves we have lying around, and the result of applying to these is actually something that we understand quite well. It turns out to be just have a basis corresponding to the fixed points of the corresponding arrangement, which is going to be a slice to a sub arrangement. So you have both of those operations going on, but it just corresponds to a natural basis of that vector space corresponds to just the bases of that arrangement, and then when you take the direct sum of all those, the endomorphism algebra of all of the resolution sheaves. Now, the resolution sheaves themselves aren't necessarily indecomposable tiltings. They're going to end up being tilting, but not indecomposable. But they're much nicer than working with indecomposables. So we work with these resolution sheaves, and the endomorphisms of that will act on this vector space by the endomorphisms of the second factor of these Homs, and also the endomorphisms of the functors or the projectors they represent will act on this vector space. And it's not hard to show that both of these actions are faithful. And so I can construct these algebras as subalgebras of operators acting on this big vector space. And these two actions commute, so they play off each other very, very, very nicely. And basically what we can do is construct explicit generators on both sides and show that those generators are interchanged by Gale duality. And so the fact that the endomorphisms of the tiltings on one side become the endomorphisms of the projectors on the other side is basically cooked into the construction of these algebras. And to produce these operators, you start with easy cases, which is if you're taking one of these resolution sheaves and mapping it to the point sheaf. So omega I would be just the constant sheaf on a point. Then this is just the cohomology, the dual of the cohomology of a fiber, and we have nice bases of that. in terms of this basis, of ES, you can write down very explicitly what they are. It's basically just once you know the cohomology of the fiber as a sort of the top cohomology of the Stanley-Reisner algebra, basically. And similarly, there's one case of the on the projective side that's easy to write down, which is that the projective corresponding to the open stratum is just a perverse low extension by zero of the constant sheaf. It's also a standard object. And then in this case, if you want to take Homs into that object, you can describe it as by looking at what it does to the largest resolution sheaf, which is and its image inside this vector space. Well, first of all, it injects into that, and the image is easily describable in terms of this. Anyway, it turns out to be the kernel of a bunch of homomorphisms to understand. So using this, you can write down explicit bases for these operators, and then well, so if you want to map to other resolution sheaves or deal with other projectives, you need a bit more understanding, but it's sort of the same type. Any questions?
Sorry. So how did you know that those functors were representable? Does that? The fives.
I mean, I think in this case it's pretty formal. So you know you do know that it has enough projectives. So yeah, I forget exactly what we said, but it's not particularly deep. But I mean, for general reasons, this thing will have enough projectives, and then these are that basically. But again, not the indecomposable projectives. But okay, so just to give you a sort of picture of what this looks like with this 3 lines with 3 lines in the plane with one of them doubled picture. You're going to have, again, 3 coloop free flats, the empty flat, which corresponds to the open part, an intermediate flat, and the 1, 2, 3, 4 flat, which corresponds to the point. And so if you take the rows in this correspond to the different resolution sheaves, and the columns correspond to the different strata that I could take these exact functors at. And so the biggest resolution sheaf has, a stalk. The functor at the smallest stratum will have these 5 points as bases, and then everything else is less complicated than that. And the operators, just to give you kind of a quick picture of what they look like, if you look at these endomorphisms acting. So, for example, if you want to map the intermediate resolution sheaf to the largest resolution sheaf, there's a map here, which on the open part is going to take your unique basis element here to E3 minus E4, or the signs that actually have to do with orientations of these hyperplanes. So I'm not going to worry about the signs, but it would take the basis element to E3 plus E4, and then it's sort of multiplicative that I would take E2 to E23 plus E24. That's it. And what this is actually geometrically doing is, if you can also think of these Homs as being certain components of a Ginsburg type convolution variety. And what you're doing geometrically is taking you're sort of finding which component you want by looking at the by its projection onto the open onto the generic part, and then you're taking its closure and figuring out what happens on lower strata. So if for people who are used to this, Ginsburg convolution pictures of Steinberg varieties and things like that, this is really sort of an equivariant cohomology version of computing those kind of calculations. And then again, we compute the endomorphisms of the projectives, and they have a similar nature to that. Okay. So I'm just about done. I want to sort of talk about some remarks pointing in the direction of, I mean, what I want to do is to what Carl and I want to do, and we started talking about this now that I'm sort of back to doing more representation theory. Hopefully some version of these things are true in other symplectic singularities. But one of the things that the techniques for the nilpotent cone and for the hypertoric case are in each case a little bit special. And so the first remark is that hyperbolic restriction also plays an important role in the nilpotent cone in the generalized Schwinger correspondence and in a Char-Mautner and so on. But in this case, you take a co-character of the torus, and now the fixed point is not a stratum closure like it is for hypertoric varieties. It's a nilpotent cone of a levy. So there's in the nilpotent cone case, there's two different things. There's strata and there's levies, and in hypertoric case, they end up being the same thing. So it has a quite different flavor. And the other thing that's really different in the nilpotent cone case is that there's an adjoint to the restriction, hyperbolic restriction functor, which is, formally hyperbolic restriction can also be given as upper star followed by a lower shriek projection from the attracting locus down to the fixed point. And then there's a natural adjoint to that, which is upper shriek followed by upper star, but that's not constructible. It's not equivariant, it's not constructible. And so what you do is you sweep it out by there's an operation of sweeping out by an action of a group and make it G equivariant. And that combination gives you an adjoint functor. The problem is we don't know a sweep action. There's not a group. These strata are not orbits anymore. So we thought for a long time and kind of came up empty-handed formally there is an adjoint to these functors, but we don't know how to describe them in any reasonable way that you could work with. And that would also be true, I think, for Nakajima quiver varieties and so on. That the Springer case is very special at having your strata actually being orbits of a group action, and that gives you a certain power that you don't have in general. We also don't know an analog of the Fourier-Sato transform. There's not. You could include the hypertoric variety into the Zariski tangent space at the origin, but I don't know anything smart to say about that space, and there's not an obvious relation between that and the corresponding thing for the dual hypertoric variety. So again, it's sort of the ingredients don't. The ingredients that you use for the nilpotent cone don't seem to generalize in an obvious way. Next remark. So I made some point to mention the fact that the resolution sheaves are independent of the choice of resolution, and the hyperbolic restriction is independent of the choice of a co-character. And the way we prove this is using the hyperkähler description of the hypertoric variety, which is instead of looking at mu inverse of 0, where mu is a complex valued moment map, and then taking a GIT quotient, you can take instead a quotient by a compact torus, but you have a third moment map coordinate. There was a real moment map which goes to the real the Lie algebra, the dual of the Lie algebra of the real torus, the compact torus sitting inside K, and then things are much more symmetric. This is describing it as a not as an algebraic variety, but as a manifold, and what happens then is that the set of parameters, so the set of etas that you can take, well, now you can not just take eta, but you can take eta 1, eta 2, eta 3, and the set of singular values of eta is now a real codimension 3 arrangement rather than codimension 1 hyperplanes that you actually have a wall you have to cross, and that means that you can actually just rotate around the singularities. But in order to do that, you need to have a description of what is the resolution sheaf in terms of this hyperkähler picture, and it turns out to be a sort of real nearby cycles functor with respect to the hyperkähler moment map, and so you just rotate this real valued function on the hyperkähler on the hyperkähler moment space and rotate it around the singularity, and then you get the independence. And similarly, for the hyperbolic restriction, you can express the hyperbolic restriction as a non-algebraic vanishing cycles with respect to a different hyperkähler moment map, because now you're talking about the torus action rather than the T rather than K, basically. And conjecturally, this should work for any algebraic symplectic quotient or a large class anyway. I don't. This is something that I'm very interested in, but it turned out, at least with my skills, it turned out to be extremely difficult to prove. And I used some quite special things about hypertoric varieties and really gory computations in coordinates to make the things match up. I mean, somehow you have to worry about the difference between the algebraic flow in locus and the kind of things you do and the kind of flows that you do in real symplectic geometry. And it's the kind of comparison which is easy to do when your total space is smooth, but you have to do this downstairs on the singular thing. And at the moment, anyway, I finally gave up trying at that to do a general proof and just did something that worked. But I now want to come back because I strongly believe that this should be true more generally. One more remark is that the set of primes for which this category is not semi-simple is nice and easy to determine. Turns out that the intersection forms on the fibers, which are what govern the semi-simplicity of this category, are equivalent to forms that were previously considered by Sheckman and Varchenko and generalized to any matroid by Berlowski and Varchenko. And they gave a nice formula for the determinant, which is a product over there's certain special flats, and you just sum some small integers. So yeah, I won't write the formula, but there is a very nice answer that's easy to compute for which primes are relevant for these algebras. And also, I didn't write it down on the slide, but there is a version of this algebra. We call these matroidal Schur algebras, and Carl and I also constructed these algebras for a general matroid that might not be representable by a hyperplane arrangement. And I proved a wrinkle duality for those. Okay, well, thank you very much, and I'll see if anyone has any questions.
Does anyone have any questions? All right, well, if not, let's thank Tom again